What if I told you that a company just convinced investors to bet $1 billion on building a quantum computer with 1,000,000 qubits by 2027? While their competitors are working with hundreds of qubits, PsiQuantum claims their approach could leapfrog the entire industry. Welcome to episode 25 of the Curiosity AI podcast. I'm here to break down the technological breakthroughs that are reshaping our world. Today, we're diving deep into one of the most audacious bets in quantum computing history. PsiQuantum, a company most people have never heard of, just secured one of the largest quantum computing investments ever recorded. We're talking about $1 billion from sophisticated investors like Blackrock, NVIDIA, and Temasek. But here's what makes this story fascinating. While IBM methodically plans roadmaps toward hundreds of logical qubits by 2029, and Google celebrates incremental breakthroughs in quantum error correction, PsiQuantum is promising to jump straight to 1,000,000-qubit system using a completely different approach. They're betting on photonic quantum computing, using particles of light instead of the traditional matter-based approaches. It sounds like science fiction, but the investment suggests some very smart people believe it's possible. Before we dive into PsiQuantum's approach, let me explain why quantum computing is so challenging and why 1,000,000 qubits sounds almost impossible. Traditional computers use bits that are either 0 or 1. Quantum computers use quantum bits, or qubits, that can exist in multiple states simultaneously through a phenomenon called superposition. This allows quantum computers to explore many possible solutions to a problem at the same time. But here's the catch. Quantum states are incredibly fragile. Any interaction with the environment destroys the quantum properties, a process called decoherence. This means quantum computers need to operate in near-perfect isolation, often at temperatures colder than outer space. The qubits themselves are also error-prone. Current quantum computers experience error rates that make them unreliable for practical calculations. To solve this problem, quantum computing companies are developing quantum error correction, where multiple physical qubits work together to create one reliable logical qubit. Here's where the numbers become staggering. Current estimates suggest you might need anywhere from hundreds to thousands of physical qubits to create one fault-tolerant logical qubit. So when PsiQuantum talks about 1,000,000 physical qubits, they're potentially targeting thousands of reliable logical qubits. To put this in perspective, IBM's most advanced quantum computer has 1,000 qubits. Google's latest system has 105 qubits. The scale PsiQuantum is proposing represents a jump of 3 orders of magnitude. Most experts believe this kind of scaling would take decades to achieve. PsiQuantum is claiming they can do it by 2027. PsiQuantum's secret weapon is photonic quantum computing. Instead of using electrons trapped in superconducting circuits or atoms held by lasers, they use photons, particles of light, to encode and process quantum information. This approach brings several potential advantages. Photons naturally resist many sources of quantum decoherence because they don't interact strongly with their environment. They can maintain quantum states over longer distances and time periods compared to matter-based qubits. Perhaps most importantly, photonic quantum computing can leverage existing semiconductor manufacturing infrastructure. PsiQuantum has partnered with global foundries to fabricate their quantum photonic chips using established silicon photonics processes. This manufacturing approach could solve one of quantum computing's biggest challenges: how to mass-produce quantum components reliably and affordably. Instead of building exotic new fabrication facilities, they're adapting proven semiconductor manufacturing techniques. The breakthrough that convinced investors seems to be PsiQuantum's claim that they've solved the fundamental technical challenges that have historically made photonic quantum computing impractical. Creating high-fidelity quantum gates with photons requires sophisticated optical components and precise timing across massive arrays of components. The company hasn't published detailed performance metrics, but the $1 billion investment suggests they've demonstrated enough progress to convince sophisticated technical due diligence teams. The massive investment in PsiQuantum reflects much broader geopolitical tensions in quantum computing development. This isn't just about building better computers. It's about maintaining technological leadership in a field that could reshape entire industries. China has been aggressively investing in quantum computing research and has demonstrated significant capabilities in both quantum communication and quantum computing. Their quantum computer systems have achieved certain types of quantum advantage in specific mathematical problems, creating urgency among Western governments and investors. Australia's commitment of nearly $1 billion in government support for PsiQuantum's Brisbane facility represents one of the largest public investments in quantum computing infrastructure globally. This public-private partnership model creates interesting dynamics where government funding validates and de-risks private investment. The involvement of NVIDIA in the funding round signals something important about the convergence of quantum and classical computing. Quantum computers will require sophisticated classical control systems, simulation capabilities, and hybrid algorithms that leverage both quantum and classical processing. NVIDIA's expertise in high-performance computing and AI acceleration makes them a natural partner for companies building practical quantum systems. This suggests we're moving beyond pure quantum computing research toward integrated quantum classical systems. The quantum computing arms race extends beyond research into practical applications that could provide dramatic competitive advantages. The first companies to achieve fault-tolerant quantum computers with sufficient logical qubits could gain significant advantages in drug discovery, materials, science, financial modeling, and cryptography. Some quantum applications exhibit winner-take-all dynamics. If you can design better batteries, more effective medicines, or more efficient solar cells using quantum simulation, the economic advantages could be enormous. This creates powerful incentives for bold investments like PsiQuantum's billion-dollar bet. The timeline competition is particularly interesting. Multiple companies are targeting the 2027-2029 timeframe for utility-scale quantum computers, creating a natural experiment in different technical approaches and development strategies. The potential applications for large-scale fault-tolerant quantum computers extend across multiple industries, though we need to distinguish between realistic near-term applications and longer-term possibilities. Drug discovery represents one of the most compelling near-term applications. Molecular simulation, particularly for complex biological systems, could benefit enormously from quantum computing's ability to naturally model quantum mechanical systems. PsiQuantum has established partnerships with pharmaceutical companies to explore quantum applications in drug development. The ability to simulate how potential drug molecules interact with biological targets could accelerate the discovery of new treatments while reducing the enormous costs of pharmaceutical research. Current drug development takes 10-15 years and costs billions of dollars, with most candidates failing during clinical trials. Materials science applications could revolutionize multiple industries. The ability to simulate complex quantum materials could accelerate the discovery of room-temperature superconductors, more efficient photovoltaic materials, and catalysts for carbon capture or renewable fuel production. Battery technology represents a particularly important application area. Better battery materials could transform electric vehicles, grid-scale energy storage, and portable electronics. Quantum simulation could help discover materials with higher energy density, faster charging capabilities, and longer lifespans. Financial modeling represents another significant application where quantum algorithms could provide substantial advantages. Portfolio optimization, risk analysis, and derivative pricing involve complex mathematical problems that could benefit from quantum speedups. Though these applications typically require hundreds or thousands of logical qubits to demonstrate meaningful advantages. Cryptography presents both opportunities and risks. Large-scale quantum computers could break current public key cryptography systems, creating both national security implications and market opportunities for quantum-safe cryptography solutions. The timeline for cryptographically relevant quantum computers influences government funding priorities and corporate security planning. Climate modeling and optimization problems represent another important application area. Quantum computers could potentially solve complex optimization problems related to energy distribution, transportation logistics, and climate intervention strategies that are intractable for classical computers. However, we should be realistic about timelines. Even if PsiQuantum succeeds in building million-qubit systems by 2027, translating quantum computing capabilities into practical applications will require additional years of software development, algorithm optimization, and industry integration. PsiQuantum's timeline toward 2027 operational systems faces significant technical and business execution challenges that shouldn't be underestimated. The technical challenges are immense. Building fault-tolerant quantum computers at million-qubit scales requires solving problems that have challenged the quantum computing field for decades. Quantum error correction at this scale demands unprecedented levels of precision and coordination across massive numbers of components. Each logical qubit requires continuous error detection and correction across hundreds or thousands of physical qubits. The classical computing resources needed to perform this error correction in real time represent a significant engineering challenge that scales dramatically with system size. Photonic quantum computing introduces unique challenges around photon generation, detection, and routing. Creating millions of entangled photon pairs with the efficiency and reliability needed for large-scale quantum processing pushes photonic technology to its limits. Similarly, detecting individual photons with the speed and precision needed for quantum error correction requires advances in detector technology. The manufacturing challenges extend far beyond the quantum processors themselves. Classical control electronics, optical switching networks, and quantum classical interfaces must all scale together while maintaining the timing precision needed for coherent quantum operations. Supply chain considerations also affect scaling. Specialized materials for photon detectors, ultra-low noise electronics, and precision optical components may face supply constraints as the quantum computing industry scales. PsiQuantum must balance leveraging existing manufacturing infrastructure with securing reliable supplies of specialized components. The competitive landscape continues evolving rapidly. Lithium-ion battery costs continue declining, and new approaches in classical computing, particularly in machine learning and AI, could solve some problems that quantum computers were expected to address. Market education remains important. Many potential customers have limited experience with quantum computing and may be hesitant to adopt new technologies until they're proven at scale. Building customer confidence and demonstrating clear value propositions will be crucial for commercialization. Despite these challenges, the fundamental technical approach appears promising. The ability to leverage existing semiconductor manufacturing infrastructure could provide significant scaling advantages compared to approaches that require entirely new fabrication capabilities. PsiQuantum's billion-dollar quantum computing bet represents more than just another funding round in the technology sector. It signals a potential inflection point where quantum computing transitions from experimental laboratory science to commercial industrial capability. The scale of investment, the involvement of sophisticated institutional investors, and the aggressive timeline all suggest growing confidence that the technical challenges of fault-tolerant quantum computing are becoming surmountable. Whether PsiQuantum's specific photonic approach succeeds or encounters obstacles, the industry momentum toward practical quantum computers appears to be accelerating. The next few years will provide crucial validation for quantum computing's commercial potential. For investors and technologists, the quantum computing sector presents both enormous potential returns and substantial risks. The companies that successfully navigate technical challenges and achieve quantum advantage in commercial applications could capture tremendous value. The broader implications extend beyond financial returns to fundamental questions about the future of computing and scientific research. quantum computers could enable breakthroughs in medicine, materials, energy, and other fields that address some of humanity's most pressing challenges. The geopolitical dimensions add another layer of complexity. Countries that achieve early quantum computing capabilities may gain advantages in scientific research, economic competitiveness, and national security applications. What's particularly interesting about PsiQuantum's approach is how it challenges conventional thinking about technological development. While most companies pursue incremental improvements, PsiQuantum is attempting a dramatic leap that could either validate their photonic approach or demonstrate the limitations of ambitious timelines. The success or failure of their 2027 target will likely influence the entire quantum computing industry's development trajectory and investment priorities for years to come. What's your take on quantum computing's commercial timeline? Do you think PsiQuantum's photonic approach can deliver on their ambitious promises, or are the technical challenges too formidable? I'd love to hear your thoughts on whether this represents genuine breakthrough potential or expensive engineering that may struggle against continued classical computing advances. Don't forget to subscribe for more analysis of breakthrough technologies that challenge conventional wisdom, and I'll see you in the next episode where we continue exploring the innovations reshaping our technological future.